Greetings. My name is Aidan Stark, and this is my ENME435 HW5 Project, a smart doorbell detection system. For this project, I was tasked with utilizing Python, OpenCV, and a web camera to monitor my front porch and record a 30-second video if the web camera detects something that has entered the area of the front porch. The details of this process will be explained later in the video. After recording the 30-second video, 2 images along with the recorded video are automatically emailed to my email account. Thus, I can be notified of activity at my front porch and see what is happening. First, I'll demonstrate the functionality of my program. Here you can see a screen recording of my laptop currently running my program. It is continuously taking 2 photos, each a half second apart, and comparing them pixel by pixel to see if substantial changes have occurred. If nothing is detected, it prints that to the screen and proceeds to monitor the environment again. If something is detected, it activates the camera and begins recording. It displays to the terminal the duration of the video recorded, then emails the user. Once the user has been emailed, it continues this process. On the left side of the screen, you can see the email that has been received by the user along with the 2 most recent images taken that triggered the system. You can see that my presence entering the front porch triggered the system because there is a substantial change between the 2 photos. It also sends a recorded video to the user. Here you can see the recorded video capturing me entering the front porch and entering my house. To get an understanding of my setup, here you can see my laptop positioned inside my house, along with the tape markings I have made to ensure that its position is replicable. Now I'll discuss the details of this process. After taking 2 images a half second apart, the program creates a mask of the image so it is only observing the portion of the image that correlates with someone entering the front porch. This is to ensure that other observances, such as a car passing by, do not trigger the system. Only stimuli within the mask. This is also why the positioning of my laptop has to remain consistent to ensure that this mask continues to align with the same geometrical features such as the column on my porch. I use a half second delay between images because I found that this provided the best level of consistent detection. Originally, I took images 1 second apart, but this significantly slowed down the rate at which it analyzed my front porch and made it more likely for the camera to turn on too late and miss the action, so to speak. Having the delay much lower, however, made it so the camera would be less likely to detect any change. If the delay between pictures is too small, then the stimuli triggering the camera has to be moving at a fast speed, or else there won't be a significant difference between 2 images taken too close together. After applying the mask, the program converts it to grayscale, performs a Gaussian blur, and decreases the resolution of the image. The image is converted to grayscale as an easy means of comparing pixels by intensity. It could also make comparisons using RGB or HSV values, but since I am only concerned with detecting a change, not a change to any particular color, shade, or intensity, grayscale is the most efficient comparison. The Gaussian blur applied to the image helps to eliminate high-frequency noise. For my setup, I used an 11 by 11 pixel kernel size for the Gaussian blur. During testing, it was found that kernel sizes of 7 or more would sufficiently reduce most high-frequency noise. Since the next step is comparing individual pixels between the 2 images, having a lot of pixels varying slightly from the high-frequency noise inherent to the camera would throw off our detection. Thus, I performed the Gaussian blur to eliminate this variable. Lastly, the resolution of the image is decreased to speed up the processing time of the system. By having less pixels to analyze, the system can process the images faster. With the 2 photos sufficiently prepared, the algorithm can finally make the comparison. It iterates in a for loop to compare if 2 pixels are sufficiently different. For my setup, a change in grayscale intensity of 50, higher or lower, was considered a sufficient difference. When observing a still scenery, pixels would tend to change in value between 1 to 5 units of intensity. As such, 50 was likely an overkill threshold and could have been lowered, but was not high enough that I was preventing a moving scenery from being detected. For that reason, this value was left at 50. The program then tallies how many pixels were sufficiently different and compares it to my threshold of 353 pixels. If 353 or more pixels were sufficiently different, then that triggers the algorithm to begin recording from the web camera. This value of 353 pixels was determined through repeated tests of me walking onto the porch and observing how many pixels were triggered, usually between 392 to 588. Due to occasional minor changes in the environment, such as clouds, up to 78 pixels would be triggered. Thus, 353 pixels was decided as an appropriate threshold that should always detect my presence and ignore slight environmental distortions. An important note that I'd like to discuss about the various parameters used in my algorithm is that none of them are absolutes in being the correct choice. Rather, they are dependent upon the situation being observed, the desired sensitivity, and the other parameters. For instance, if I use a smaller kernel size for my Gaussian blur, then more pixels are going to have more high-frequency noise. Thus, I have to increase my grayscale pixel intensity difference threshold when comparing images to account for more pixels experiencing that noise. Alternatively, I could increase the number of total pixel changes needed to begin recording. My point being that any one filter can be decreased by increasing the other two, or vice versa. Thus, there is no singular best option of parameters for this algorithm, only good combinations of parameters. For future work, I would experiment with trying to create variable thresholds with light intensity. While experimenting, my work took place during different hours of the day. During brighter hours of the day, the program could utilize a much lower total pixel difference threshold than darker hours of the day. At dusk, I need a threshold of 980 pixels to properly detect the user. To improve the system, I would want to take the average grayscale intensity of the image, determine the brightness of the setting, then make the total pixel change threshold proportional to that mean grayscale intensity. This has been my ENME435 Homework 5 project. I'm Aidan Stark, and thank you for watching.